So we're looking at higher derivatives today. We're going to look at a couple different notations of how to write it and then applying the rules we've already talked about in order to find derivative. Okay, since the derivative, who's not muted?
Yes,
I have recorded,
but I hear myself.
not muted. Palm Bear? Excuse me. Sir. Mute. You're going to ruin my beautiful videos. Okay. So since the derivative of a function is denoted with a little f prime, assuming our function is represented with the letter f, we can take its derivative. We can now essentially substitute. Rather than taking the derivative of f, we can take the derivative of f prime. And the result is called the second derivative, or f double prime. Essentially, the number of primes next to the letter f denotes how many times we have taken the derivative. However, it gets a little bit messy once you go past 3 derivatives, because then you have to like carefully count how many ticks there are next to the letter f. So there's other notations that we use. This is an example of Leibniz notation. Leibniz is a mathematician who we will not learn about today, but you should know who he is and what he has done. And I think I have a poster somewhere on my wall that we can read about it later. Okay, so Leibniz notations uses the d by dx notation, and it uses a number to represent how many times we've taken the derivative. So if you see a little 2, then we have taken the second derivative. It's just a 3, you can take the third derivative, and so on. Okay, the rules that we have learned still apply. We just do one derivative at a time, and we just keep on going. So for example, let's start off easy. If y is x to the power 6, what is it? The double derivative, meaning, or the second derivative. So y prime, we do the power rule. This is 6x to the power 5. Now we start here. Assume this is our new function. What is the derivative? Or what is the second derivative? We apply the power rule again. Bring the 5 down, multiply the 6. We end up with 30x to the 4. And you can keep going. What's the triple derivative? What's the quadruple derivative? And on and on and on and on. You just keep applying the derivative rules as you go. So this would be what? 120x to the 3. This would be 360 x squared, right? And you can just keep going. In fact, you can keep going as many times as you want. You can go up to the 20th derivative if you wanted. But as you get lower, right, we're going to have x to the negative 2, x to the negative 3. You can just keep applying the power rule. It'll get uglier, but you can still do it.
But then there's also the rule that like the derivative of a constant is 0.
True. It does end at some point. We're going to do ones that don't end. They're going to be beautiful. You'll love them. Let's keep going. Example 2. Find the second derivative of this function here. What's the first derivative? What's f prime? This is a sum rule, right? We can treat those 2 pieces individually and add them at the end. 10x plus 1 over 2 root x. Okay, second derivative, same thing. However, I'm going to write this in power notation because power notation is always easier. So sorry, plus 1 over 2 x to the power of negative 1/2. What would be the second derivative? 10 minus 1/4, right? Because 1/2 is 1/4. One of them is negative. And then negative 1/2 minus 1 is now negative 3/2, right? So this answers the question, what is the second derivative? Can you do the third one? What would it be now? What's the derivative of 10? 0. Okay, but we can do the other one. Bring the negative 3/2 down. What's my coefficient?
3/8.
3/8 positive x to the
negative 5 over 2.
-5/2. Right, and we can do the 4th and the 5th and the 6th. As long as we understand how the rules work and we don't end up with just a constant, we can keep going. Sometimes you have an equation where you can just keep going forever and ever. Sometimes it repeats itself. Sometimes it goes to 0 because you just end up with a constant at some point. All right. Example 3. Here is my function. I want the second derivative evaluated at 1. We are going to do the derivative rules. Yes, sir. Yes. Correct. The power represents how many times we derive it. Because when we say take a derivative, we are saying the derivative with respect to x of a function f of x. So this is the thing identifying the derivative. This is what we're taking the derivative of. So we're not squaring the function. We are taking the derivative 2 times. Does that make sense? Yeah, so it's a little bit different notation there. Okay, example 3. We are going to take the derivative 2 times and then substitute x equals 1. As you can see, this is a chain rule. This is my inside function and the power is my outside function. So f prime equals chain rule.
So it's going to be 10 and then the inside unchanged.
Inside unchanged times
9 then times the inside changed.
inside derivative is what?
Negative 2x.
Negative 2x. Okay, so this is chain rule. Derivative of the outside times the derivative of the inside. Now, when we go to do the second derivative, not only do we have a chain rule, we also have a product rule. It's this times this, so we can call this G and this H if you like. So we have chain rule and product rule. Let's see if we can do all of it in our head by reading and squinting slightly. Okay, derivative of the first one, what would it be? 90 2 minus x squared to the 8 minus 2x times minus 2x.
You can just write that as 2x squared, negative 2x squared.
Right, so this is chain rule derivative of the first item. This is the second item unchanged, right? So we can call this G prime H if this was G and this was H. Plus product rule, we now need H prime G. What's H prime? Just minus 2. And G unchanged is just 10, 2 minus x squared to the power 9. Now, if I were just leaving it as a second derivative, I would collect like terms, simplify as best as possible. However, I don't need to do all of that because I'm evaluating it at f double prime of 1. So I'm just going to do direct substitution and not worry about simplifying it this time. So this is 90 bracket 1 to the power 8 times positive 4. I can do some of this in my head. Plus negative 2 times 10 times 1 to the power 9. Right, so I'm substituting every x I see with a positive 1. So f double prime of 1 equals 340. Wonderful. Questions, comments, concerns? Okay. Okay. Question 4. What rules do I need here? Product, anything else? A trig, yeah. So let's call this G, let's call this H, and we're going to do a second derivative. So F prime, derivative of the first, second unchanged, plus the first unchanged, derivative of the second. To do F double prime, or the second derivative, I can leave this on its own and just take its derivative is going to be negative sine x. It's not multiplying or dividing anything, so just leave that alone. However, here I have again a product rule. So derivative of the first times the second unchanged plus the derivative of the second times the first one unchanged. And here is where, because I'm not evaluating it at any point, I am going to simplify where I can. I see I have a negative sine x and a negative sine x. So this is negative 2 sine x minus cos x cos x minus x cos x. So this is my F double prime. Questions, comments, concerns? Okay. Note, the acceleration function is the derivative of the velocity function, right? The way that we define acceleration is the rate of change of your velocity. The way that we define velocity is the rate of change of your displacement. So we can note these are true statements where S represents displacement. Okay, so in example 5, we have a word problem. A position of a particle is given as this function, depending on time, where t is in seconds and s is in meters. T in seconds, s in meters. Find the acceleration at time t. Acceleration represents the second derivative of displacement. We want the general acceleration, and then we want the acceleration after 4 seconds. So if s is t cubed minus 6t squared plus 9t, then s prime is the same as velocity. This is going to be 3t squared minus 12t plus 9. And therefore, S double prime, which represents acceleration, will be 6t minus 12. This is the general acceleration. What will it be after 4 seconds? Well, then we just use substitution. Acceleration at 4 seconds is 6 times 4 minus 12. I want to say it's 12. Did I do that right? Did I math correctly? Yes, I did. Okay, next thing, yes. Because it asked us for acceleration. Acceleration is the rate of change of velocity, which is the rate of change of displacement. So we have to take 2 rates of change, 2 derivatives. Velocity is once. Yeah. Right, the other way you can think of it is S represents meters. S prime, or velocity, is changing meters per second. And acceleration is meters per second, or meters per second squared. Okay, graph the velocity, position, velocity, and acceleration for time between 0 and 1 second. So what we want to do is essentially sketch a graph of what's happening in the first 5 seconds. So with our graphing calculators, you can put the S function into Y1, the V function into Y2, and the A function into Y3 for our graphing calculator. So I'm going to take a moment here and do that. And I'm going to give you a bit of a head start. We're going to then go to table and do a table of values for all 3 of these. Okay, so I'm going to my y equals, and I'm going to type in y1 the displacement, x to the power 3 minus 6x squared plus 9x. And y2, I'm going to write my first derivative, 3x squared minus 12x plus 9. And then I'll have 6x minus 12. I then double check that my table is not on auto. I want it to ask me what values to choose. So I'm going to go second table set or second window. It is on ask, perfect. So then I go to second table. I'm going to write 0, 1, 2, 3, 4, 5. Okay, so I can read off this list my y1, which represents my displacement, my y2 represents my velocity, and then I'm going to move over and you'll see y3 will have my acceleration. So I'm just going to minimize my window here. Ooh, this is hard to do without a keyboard. Let me attach my keyboard. Where is it? Okay. So at time 0, my displacement is 0, then 4, 2, 0, 4, and 20. My velocity, 9, 0, negative 3, 0, 9, 24. And then I'm just going to go over to y3, negative 12, negative 6, 0, 6, 12, 18. There we go. Okay, I am going to draw my displacement in green. I will draw my velocity in blue, and I will draw my acceleration in pink/purple. Okay, so on my grid, starting at 0, what's the highest number I need to get to? 24? Oh, geez. Let's just pretend. This is 24. 1, 2, 3, 4, 5, 6. So 1, 2, 3. This is 12. So this is going up by 4s. 8, 4, 16, 20. Okay. I'm only going up to 5 seconds, so let's spread it out a bit. Let's say 1, 2, 3, 4, oh, so close, 5. So in green, I start at 0, 0, 1, 4, 2, 2, 3, 0, 4, 4, 5, 20. So here is the movement of the particle in terms of displacement. Then I graph my velocity. At 0, it is 9. At 1, it is 0. At 2, it is -3. At 3, it is 0. 4, it is 9. And 5 is at 24. And lastly, the acceleration. 0 is -12. At 1, it is -6. At 2, it is 0. At 3, it is +6. And at 4, it is 12. And 5 is 18. Oops. Okay. Take a look at our final functions. It will take your phone away. Both of you. Because you're not doing notes. Thank you. You aren't. Okay. Take a look at what I've sketched out here. The green looks like what kind of a graph? Okay. The blue looks like what kind of a graph? And the purple looks like linear. Does that make sense? Yes, because I start with a cubic. When I derive, I drop by a degree. I end up with a square. And when I derive again, I end up with a linear function. That is the correct way it should look. Now let's look at some comprehension questions. When is the particle speeding up? What am I asking? When is the acceleration increasing? The slope of the acceleration is increasing.
Right.
But it is not increasing the whole time.
Wait, it's increasing at, it starts increasing at t equals 2. Starts increasing from there up till.
Yes. So basically, when is it speeding up is when is acceleration greater than or equal to 0, right? So because we're only focused on the time period of 0 to 5, which is our picture, acceleration is positive. It is speeding up between 2 and 5. Similarly, when is it slowing down? What am I asking? Where is it lower than 0? So this will be between 0 and 2. Okay, the other thing I want you to notice about all 3 of these graphs is that starting with the green graph, this point at 1 represents a 0 slope because this is where it was going in the positive direction now and stopped and turned around. This also corresponds with a 0 on the velocity graph because it's the slope of the top of that curve, right, which is a horizontal line, which is 0. Similarly, when I'm looking at the bottom of the velocity, when it changes direction here, it goes from negative velocity and it's coming back up to the positive. This represents a 0 on the acceleration, right? The derivative will always have an x-intercept where the original function changes direction, essentially at the tops and bottoms of the peak. That is a really key point there. Okay, let's flip the page. Higher derivatives can also be defined. We can, of course, do third, fourth, fifth, and nth derivatives. The nth derivative means put in whatever number you want for n. Can be denoted, this is our Leibniz notation, and this is big D notation. I know, it's very, very funny when I say that. Okay, so either notation works. It is a shorthand method or a short term for writing the nth derivative of whatever function that you want. So I will leave you to do this in class right now. What are the first 5 derivatives of this function? First 5 derivatives. Take a moment. Yep.
Everything past the first derivative is 0.
How do you know that?
It's 5, so eventually it's going to get to 0.
Yeah, the first derivative will take care of that. The second derivative, that goes away. The third derivative takes care of that. The fourth derivative takes care of that. So you really could just focus on this one and do 5 derivatives of this.
But then it wants us to state all the 5 derivatives.
Go on. You can do it.
Yeah.
After 3, this just becomes ridiculous. I'll just use 4s and 5s there, because then I have to start counting how many ticks I made. Tell me what the 5th derivative is.
4.
How do you know it's 0?
It's 4.
It's not 4.
No, I know.
It is 0, right? Because the first 4 derivatives will bring this down to a constant. So the 5th derivative is the derivative of a constant, so it's just 0. Right? And you can do all the steps in between to prove it to yourself if you like. Okay, let us get into an uglier example. Implicit differentiation, we want the second derivative. Implicit differentiation. The first one should hopefully be more or less straightforward. Oh, oops. Sorry. If we take d by dx of that in here, this will give me 3x squared plus 3y squared, y prime equals 0. Y prime equals negative x squared over y squared. Are we okay with that? Okay, trickier when it comes to y double prime, because we are going to have a couple of substitutions. This will represent y prime. We will have to put that back into y double prime when we get to that spot. So y double prime, now I have quotient rule and implicit. Quotient rule plus implicit. So if this is f and this is g, what's the quotient rule tell me?
So the numerator will have the negative
G of derivative minus
G derivative f.
minus f
all
d
of
derivative.
Right. Okay, so now let's do a quick aside here. If f is negative x squared, then f prime is negative 2x. if g is y squared, g prime is what? 2yy prime. And 2yy prime is 2y times negative x squared over y squared,
Or just.
right? Because y prime we already solved for. So we want it in terms of x's and y's. So when I go then to substitute stuff, I'm using this one, this one, this one, and this one when I do my substitutions. So y double prime is y squared times negative 2x minus 2y times negative x squared over y squared, bracket, what's f? X squared, all over y to the fourth. Correct. It's gross. Let us simplify where we can. There's a y in the numerator and two y's in the denominator, so those cancel out. I have a minus x squared, which will cancel out that negative, and then I can make it an x to the fourth with that. And I think that's all I can do. Y double prime is negative 2xy squared plus 2x to the fourth over y, all over y to the fourth. And you could even multiply y and y so that you don't have a stacked fraction. So you would get negative 2xy to the 3 plus 2x to the fourth all over y to the fifth.
You can factor out a negative 2 as well.
You could factor out a negative 2. You can even factor out a negative 2x. That would be fine, but it doesn't make anything any simpler, right? Okay, that wasn't actually too bad. Hooray! We can do calculus. It's beautiful. Oh, you could make it even simpler.
Yeah.
You could take, let's see, y cubed is 5 minus x to the cube. You could make it, yeah, I don't want to, but you could make it even simpler. Yes.
Shouldn't the x squared be negative?
Where?
Like f, where it's g times f, and there should be negative x squared.
No.
Okay, the numerator is negative.
Right here?
Yeah.
Yes, because this is negative. Sorry, yes, that should be negative, which means this is a negative. Yes, sorry, good catch. This was a negative x squared, not a positive x squared. Yep. So you could simplify this further by substituting y cubed because y cubed is part of the original function. I'm not going to ask you to do that. However, I am going to ask you to find the pattern and tell me the 27th derivative of cosine x.
Wow.
So you're going to take the derivative until you find a pattern and then tell me what the 27th is without actually doing it 27 times. Yes, but there are negatives involved. So find the pattern. Tell me what the 27th is.
It's going to be negative 9.